have a string name for this topic. It's called a heap. Okay, so a heap is not a binary tree heap in your data structure course. Okay, it's totally different thing. And heap here only means a pile of things, a group of things, and that's all. Okay, it's nothing concerned about a complexity, a binary tree, so on and so forth, and it's just a place in your main memory, or I should say your process memory to be exact. Okay, it is your process memory. There's an area here, a huge gap, really huge gap. It depends on your architecture. You're using 64-bit CPU, then it will be a huge gap here. So that's structural scale in this figure, which is originally unallocated. Then you can touch this area only through the heap management. Okay, the heap management is brought to you by the malloc call, okay, and the free call. Then you always use it. Okay. So the allocation means that it's dynamic. It's only on your request. And the compiler won't do anything for you, unlike the global, the scale, okay? The global and the kernel compiler do everything for you. It's constructed. Now the heap is left blank, and you shouldn't touch it. When you touch it, you will get segmentation faults, okay? Because you didn't allocate anything. And allocation is to be given to you only when you ask for it, okay? You don't ask for it, segmentation fault. If you ask for it, you touch it, okay, fine. It is both readable and writable. Yet, if you go beyond certain boundary, then you will get another segmentation fault. So later on, I will have a small diagram to explain to you. And small diagram is just a few slides later. So I also want to explain to you something about the malloc and free. Okay. So how many of you don't know what is malloc and free? That's okay. My year one course don't talk about it. Okay. Maybe your data structure course didn't talk about it, then will be a disaster, right? Because now it's entering your third year. The first time you hear about what is malloc and free. Okay. So, but every course, okay, maybe you're not learn from here. You learn from Coursera. You learn from other sources. They usually tell you one thing. The thing is, the malloc is an allocated memory for you. That's all. Okay. I would say the answer is yes and no. Yes for some time, no for some other time. Okay? Malloc is beyond your imagination. It's totally a piece of crap. Very, very complex. And to free, sometimes you encounter this a lot, okay? Raise up your hand if you encounter this. How many of you have tried free and then you got segmentation faults? Yeah. So this guy, every C programmer, right? Because whenever you encounter this, what you do? You don't call free. Right? Yeah, that's free, this one here, I don't call it, okay? Yeah, so this is a little bit strange here, right? Because people tell me that free is to deallocate memory. Why deallocation give me segmentation faults? It seems to be strange, huh? It's because deallocation is not just simply look at your previous allocation record and delete it. Okay? It's actually maintained in a very strange way. So this course is to, I would say, to redefine what is in your mind. Okay? Really redefine everything about malloc and free. And from now on, you will start to hate malloc and free. And you will try to avoid it. Like me, I always avoid it. If I have a problem I have to solve, I would prefer using global verb. Okay? Or hard code. Okay? Really want to avoid. Now let's talk about what is this guy, okay? That guy started with one system call. Okay? These two guys actually calling the same system call in order to control the allocation and deallocation. Okay? And the system call is to govern this area. Okay? This area, we call it empty heap, nothing. So whenever you touch it, you get some segmentation fault. Now how to grow your allocation, we will use a system called break. BRK, break. I have my Linux get ready here. Okay. So always get blank screen. So this is my Linux. So this is a 64-bit Linux, no problem. So this is a brick system call. The description a little bit strange, right? It's not called a heap, but I call it change data segment size. Okay, and there is a kind of a frame of it. Okay, the brick system call and the SBRK. So the S brick system call. The one system call with two flavor. Okay, the one of flavor is using pointer. One of the flavor is using the increments. So what is the meaning? You can set an increment here, then the increment will change the following. The following thing is this allocated level. Okay? So you said that you want to increase by 10 bytes. Then this level will grow by 10 bytes. If you want to say the SBRK call, the S-brick call, you want to have a negative increment, so then it will drop. So you can control this level. And that is working behind screen about using the malloc and free. Okay, malloc is to grow, free is to drop. Okay, drop this allocation space. It seems to be easy, right? Yeah, but can you find something wrong here? When you use malloc, okay, you're not controlling the allocation space, right? You seems to be having a block of memory that belongs to you. And another block belongs to your memory. Someone tell me that, oh, this block A and block B, you call to malloc, they are totally separated, and don't try to get beyond that boundary. It seems that the whole statement that I said only works and only match with the one keyword, boundary. Right? You can see clearly that there is a boundary, but there is no block concept here. Right? I just said that there is just a water level. Yeah, you control the water level. And all that little blocks is living inside the pink area. And malloc call and the free call is the management of those little blocks. Okay? So this is grow and shrink. So what is the management? The management is very complicated. So different compiler, as I say. Different compiler give you different surprise. Okay? So what is this program is doing? I imagine that you accept that's why I said imagine, because the level is not easy to understand, right? And imagine that you already accept that, okay, there's a level changing, and what is the malloc? Malloc is kind of crazy. So I don't want to use a Mac to demonstrate it, because Mac use a different implementation. I want to show you this program using the 64-bit CPU as well as 32-bit CPU on Linux. Now, when you look at this program, you see I allocate two little guy, very little, right, 16 bytes only. And these two 16 bytes, if I imagine this is following this rule, you want to grow 16 bytes, okay, I give you 16 bytes. Then I give you another 16 bytes. Because I'm here only grow up to 16 bytes, you should grow more another 16 bytes for me, so that I can allocate this two area 32 bytes, right? So how can I know what is the distance between these two guys? Okay, that is fortunate. Okay, the fortunate thing is this two pointer is the return value, supposed to be the address in this heap area. Suppose, okay. So we can rely on this pointer to do a subtraction. Then I will know that whether the two allocation is it come back to back or no. Okay, let's go. So understand what I'm going to show you. Okay? So first I'll let you see it. Okay, so the same program. This time I have one more. So one is 1 to 2, and another is 2 to 3. It's the same thing, right? Same thing. Let's go. So what do you expect? What's the meaning here? What's the meaning here? I've got a two allocation, should be side by side. One guy with another guy should be side by side, but the distance is not 16, right? The first guy, you give me I maybe use a drawing board to demonstrate to you. Okay. All right. Okay, suppose it's something like this, right? You call the allocation P1 here, which is 16. Okay? And then if it comes side by side, it should be another allocation P2 and another 16. And if you understand what's malloc, malloc is giving you the beginning address of the two blocks. So the distance should be 16. But what my Linux tell you, my Linux tell you is 32. So what is the meaning? The meaning is this is not P2. P2 is here. Oh, no, I should say another pointer. Okay? So rub this out. So it means from here to here there is a big gap between the P1 and P2, which is approximately 16, not approximately, exactly, okay? Exactly 16 bytes. Okay? Now, this is for the case of what is the CPU? This CPU is a 64-bit CPU. Now I go to 32-bit CPU. Okay? This is the result of 32-bit CPU, the same program. Now this time it's not 32, but it's 24. Okay? So, well, it seems to be very strange, right? But its end up is like this. Its end up is like this. The malloc is silently doing something. Okay? It is doing the allocation like this. The deep red block is something secret that you don't know. Okay? There is a secret hiding there. You don't know what it is. And the paint area is the area that's supposed that I return to you and you can use it. Okay? And there are two management blocks. And the management block is of varying size, depending on your architecture. You're using 32-bit architecture, the old architecture will be 8 byte. Okay? Will be 8 byte. And this architecture, what is storing? Or it doesn't mean that, it's not for buffering, okay? Some people think that, oh, it's so buffering, okay? Malloc is so smart, okay? They know that we suck, okay? We write program only to go beyond that, okay? Yeah, okay? Please don't believe in that, huh? You say, no problem, the malloc give me something more, okay? Keep writing, yeah. I know somebody is doing that, okay? And as long as the program can run, no problem, okay? Yeah, that's not the case, huh? This management block is very important, and let's take into a deep look into this management block. Okay? So any problem you want to ask until now? Okay? I cannot demonstrate it in Mac because Mac using another allocator. We call this a memory allocator. The memory allocator, I didn't read any of the material yet. Okay? Because when I found it strange, I don't have time to investigate. Okay, so this is the result from Mac. Okay, Mac behaves strangely. It seems there's no gap in between. Okay, so I have to look up some documents in order to understand why. Okay, so let's take a look at what this guy is doing. Before this, let's also investigate what is the probability of we get a free core give you segmentation faults. Okay, really the probability, right? You sense that sometimes maybe you are kind of referring some people's work, okay? And your program don't have any problem calling free, but his problem is whenever you call free, the program crashes, okay? So let's see what is or why it get into this trouble by looking at this diagram, okay? Now remember what is the free call, right? The free call is you use this pointer, the pointer pointing to the previously returned address from malloc. Now this is the must, okay? This is a must. You cannot say that, I know that this is a problem, okay? Let me point to whatever location. And the malloc should know that this belongs to him, no. Because why? This is the point that you feed into the free call. And a free call is just it is a 32-bit CPU. It will just do a decrement of 8 bytes to refer back to this management block. Okay? And let's say you are going to free something. You are going to free something. And the guy that you want to free is at the end of the heap allocation. And this is the end of the allocation here. It's end. The white area is the area that you didn't claim. Okay? Remember, when it isn't claimed, you can access it. So the free call is very easy. Just try to change it. Okay? Change it. Change the allocation size from this area, this bigger area, to this smaller area. Okay? Now, how about another chance? The other chance is you say that, okay, I don't want to deallocate this, but I want to deallocate someone in between. Now, that's funny, right? When you try to deallocate someone in between, are you going to do this? You should not, right? You should not just say, yeah, I know that this is the point that you want to deallocate, so I will destroy this as well. Yeah, just change it, okay? Then later on your program call that area and immediately touch this white area and get that segmentation fault. No, that's not the implementation. Okay? The implementations have to update instead of doing a blind changing, okay, refly. Okay? We go to another approach. The other approach is to use this management now. Okay? And you will see why sometimes you will have some management faults, sometimes not. Okay? So this management block, imagine that we cut this area in two. Okay, cut this area in two. I just write in a bad way. Okay, it's supposed to be two side by side, just like an array. Each of them is of the same size. If it is 32-bit CPU, okay, it is each of them is 4 byte. If it is a 64-bit CPU, each of them is 8 byte. Okay, and what are the two guys? One guy is storing the size. Okay, supposed to be the size of your block. And other one is a pointer. Okay, and what this pointer is supposed to be forming a linked list. And later on, I will tell you what is that linked list. Okay, so this is important, right? Let's say you're doing free. Okay, you're doing free, and you give me this pointer area. Okay, I want to destroy that. I am the implementation, okay, I'm the code, I'm the implementation of free. At least I want to know how big this area is, right? Or I don't know by how many I need to change. So that's why I remember the size of your previous allocation, 16 in this little area. So that I know that, you're going to destroy 16 bytes, okay? I changed by 16 bytes. Now I don't want my management block anymore because the memory is gone. So I'll also change 8 more bytes if it's 32-bit CPU. Okay, so get this idea? Now, what is this pointer is doing? This pointer is to serve this scenario. This scenario is easy to serve. When you say that there's something in between, and you don't want it, but you cannot change it, okay? Then we will have a head, which is a global variable, hiding in your, how can I describe it? You have a standard IO.h, right? Or standard library.h. It's from the library, right? And actually the library has allocated a global variable, and a global variable is a head pointer to point to your process. Remember, it's your process. And to where in your process? To the linked list of the free allocation list. Okay? You want to free it, so I cannot change it. Sorry, I don't want to give you up. Okay? You can give up. Yeah, you want to free it, but you cannot change. Yeah, let's give it up. Okay, just leave some memory there and we introduce the memory link there. No, we don't want to link any memory. Okay? We will have one global variable setting up a linked list. Manage this guy, and I know that next time you want to have a 16 bytes again, what should I do? I reallocate this block to you as just like a random friendly or recycle memory for you. Okay? So then this will be non-null. Sorry, this guy is non-null, okay? This is non-null pointing here, and this guy serves as a pointer, so no next block. So I say this next is now. Now, if the storage continue, let's say I'm naughty, I call the free alternatingly. Okay, alternating free pattern. Okay, so what is the new heap? The new heap become this guy is supposed to be the end of the heap. I will change it. I will change it. Change the heap allocation area. For others, in between, I will set up a linked list. Starting from the global variable inside your GNUC library, point to the first guy, and the first guy say that, okay, I know there is the next block. I use pointer address, okay, or I should say address, to put it here, so that I can form a linked list of free memory, free list. Okay, we call it free list. And this free list, later on you will see it's being recycled. Okay? So any question about this? Any questions? You shouldn't have it. Yeah.
If next time I allocate like 10 bytes or 32 bytes.
32 bytes. Okay, so if it's 32 bytes, then there's no free guys in between. So I have to allocate an n. I cannot say that, okay, you go to here, or you go to here, so that I make a continuous area. No, because this middle guy contains a pointer that is used by your program, right? Then I can ask the program to change now from this moment onwards, your pointer address string from A to B. So I cannot do this. So I have to allocate here.
What if all the holes are small, but their amounts can contain the big byte, but there is no last space to can contain.
You can combine all the holes if they're continuous. If not, then we'll have an external communication problem. Yes, that's true. Okay? And actually, malloc is a very bad guy, right? You can see here, if I have this linked list and this two classmates always keep on saying that, hey, what happens if I do allocation? What if I do allocation? Actually, there is a one-word straightforward problem is, if I want to allocate, what is the complexity, the time complexity that I need? If I don't have previous allocation, pick off n, right? Always start with the n of the throw it, okay? But if I have some free space in between, then the allocation speed will be slower and slower. Okay? Because every time I'm scanning through this list, okay? I don't know how to organize it. Maybe you build an index, build a heap, or whatever things you want, make it into big of big of n, big of log n. But this is not the concern. The concern is you have to search. Okay? You have to search and cause your malloc slower and slower. Okay? So actually I haven't done an experiment that I just cut out those slides. Okay, I know that I don't have time to explain it. You can do a same experiment as I do. You can do, let's say you build a linked list. 1 million node, okay? 1 million node. Then you free them alternatively and reallocate them alternatively again. Okay? So you will see some speed difference if you keep the free list or don't keep the free list by you implementing it by yourself. Okay? And also through the malloc call itself. Any question you want to ask? No? Okay.
Excuse me.
Yes.
So here, each block is 16 bytes.
Yes.
Am I allowed to like call free from somewhere in between?
No. I just want to explain to you why you cannot. Yeah. Okay. Some precaution, this customer already mentioned is, this is the area that you can play with, right? And now you know that why it is dangerous if you write your memory outside your allocated area, because you are going to touch other people's management block. Okay? Let's say you are going to write zeros to your blocks, but you go over it, then you will start writing zeros in this area to set other people's management saying that that block is zero size, or that block the linked list of the free list is null, okay? Then this is a peaceful case. If you are not writing zeros, you're writing some random numbers, then you'll be very happy, okay? Random numbers, then you create a free list pointer pointing to nowhere, and then while the malloc call wants to malloc new memory for you, it will jump to I don't know where, but get something to the point. It's also for the case for free, because you have to build this linked list. Okay? If I want to build this linked list, you call free, but you override some of the management blocks. Sorry, you corrupt the free list. While I'm transversing it, I get some segmentation faults. So that's why when you encounter some trouble in debugging your program is caused by free, it's not caused by free. It's caused by you. Okay? You are writing out of bound, okay? And without awareness. Let's say you allocate 10 bytes, but you write 18 bytes, definitely wrong. But you don't know, okay? So every time how I tell people to debug, okay? How I debug, first I need to tell them it's not the problem of free, okay? It's your problem. So I tell you that, how about every time you grow your allocation by 16 times, okay? Yeah, every time you times 16 there. Then those guys will happily find that, no bug. Then you know why, okay? Because they write more than they need, okay? I just give a random number 16, okay? And they believe in it, every time we get 16 by more, 16 by more, then I have no problem. No, it's not no problem, but you are just lucky, okay? Now, another precaution is solving your problem. What happens if I have this area and I say that, okay, how about I free the memory block, but I give you this location, this red arrow location, but not the start of this block. Now, you can imagine why it's failed, because when you give me a pointer, okay, so what I'm going to do if I'm the library, I'm doing this. Okay, so maybe not a good way. So if I'm a library, let's say this is the implementation of free. Okay, implementation of free. Let's say something like this. Okay, so you give me a pointer. So I will go to have a management block starting address by calculated by pointer minus 8 or pointer minus 16. In order to go back to the previous, supposed to be the area of the management block, okay? So, or I shouldn't use the hard code, maybe there's some structure there, I don't know what it says, let's call it structure x, okay? A size of, okay? And this is the code illustration. If you cannot get the code illustration, this is a picture that you will decrement it and treat this purple guy to be the management block, and then you will get segmentation faults. Okay? Because this area will tell you that, I have several size, maybe 1 million, okay, and my pointer address is somewhere, okay, and you follow it, you will get a wrong case. Okay? So that's why you cannot free in the middle of it. You can only free from this point, so that when you do the decrement of the pointer, you won't get any problem. Okay? Any problem? Yeah, this is a typical implementation which is very old. The current implementation may not be like that. Okay, just like the Mac. Mac uses LLVM architecture, so they use it in other way to LLVM memory. Okay, so I didn't read the document, so I don't know what they're doing behind the screen. Okay, so this is about only calling malloc, only calling free. But now how about the recycling? Is the time that when you have malloc and free works together, okay? Works together, then you need to recycle. Now, the recycling things, let's say that several problems that the classmate asked. What if I want to allocate like this, based on this linked list, I want to have a free block get allocated, but based on my allocation size. Let's say I invoke malloc for 2. Okay, I want to have a bigger allocation, so you will not find anything like transversing this linked list, because this linked list always report to you that, hey, 16, sorry, and I have to allocate for 2 by growing the break, we call it the break, okay, or the heap size, okay? If it is 16, then you will have a reallocation of your area here. Okay? So, I think you want me to demonstrate to you, but I already skipped that slide, okay? So I can write a program now. Okay? So I just removed that. I'm afraid that I don't have the time. Okay, so what you're going to do, first of all, let's save it to haha. Okay. I always love to call it haha. Okay. Okay, then what you're going to do, 3 pointers, P1, P2, free. Okay, and later on I will copy to Linux. Okay, because only Linux works. Oh yeah, I didn't enable the clipboard sharing. Okay, yeah, better write it here. Okay. Yeah, give me 3 minutes. Okay, yeah, you can start counting. P1, P2, 3-pointer, as well as P3. What you're going to look for is I allocate 16 byte here. Okay, maybe bigger this time. Okay, 32. Okay, 32. Sorry, only 3 times. Okay, so if I'm doing this, you will understand that I create 3 continuous blocks. Now I don't want to do this. What I'm going to do is before I allocate P3, I free P1. Okay? Then what will you expect? The address of these 3 guys. P1, P2, P3. Okay, what will you expect if I do this? Let's see it. First, show it here. Can you see the first and last pointer? They are the same. You will reallocate it. Okay? So you may be wondering, hey, how about the reallocation is change from 32 to 31 byte, okay? It's not satisfying the whole block, okay? But I just leave one block unattended, one byte unattended. So where you will get this recycling result or not, let's see it. Okay. Make. Run. Still the same, okay? But bigger, you understand it's not the case, right? If it's bigger, 40. Okay, then run again. What? Wow. Oh, then must be not, okay? Is it because it's reserved some more space? Okay. Yeah, these are dig into the reason why. It's just kind of a keep more memory than I thought. Okay? Wow. Next time I better get prepared before you come. Okay? So yeah. So then we show you some little features. Okay? What happens if I use out all memory? Okay? Previous show using global variable is fun, but not fun enough because I coded into the code. I said that inside the code I have 3 GB. Now this is based on memory. Okay? Yeah. Guys, always see some funny face and what is this? Okay. So let's ask you one question. Okay. So what will you expect? We call it OOM. Okay. There's an OOM error. When you type OOM in Google, you find a lot of things. Okay. What will you expect if I write a program like this? What will you expect? Yeah, this is a memory leak program, okay? Memory will leak. Because every time I allocate a program, I use a pointer to receive the results, and then I forget the pointer address immediately. Okay? So the memory keeps leaking. And what does the mean of leaking? Because you leave it unattended, but it's already allocated. So it's not because you leak it, then it will be free, okay? That is Java. Okay, Java is using a garbage collector to find is there any pointer address which is not attended by having a variable point to it. If yes, delete them or clean them. But in C, there is no garbage collector. The garbage collector is to recycle those pointers that you forget. C don't do it. So if this in your mind, what would be the results? Computer reboots. Segmentation faults. Or nothing happened. Or you don't want to try that, okay? I tried it. No problem, huh? Yeah, no problem. But of course I will find a department computer to try it. Yeah. Yeah, because my VM don't have enough memory to try. Okay, my VM is only that field, okay? Yeah, then you are not happy with it, right? I know. Let's find some happy computer, okay? Okay, so find a department computer. Yeah, of course. So that's department should fire me. I always do damage. So which one? Which one? You know that there's a lot of people in there. 2 are. 13. No, I want a 32-bit CPU first to demonstrate a small amount. It's a free is a 32-bit. Oh yeah, this 32-bit. Okay. So let's see how many people are there. Oh, very few. All are tutors. Let's kill them. Okay, we got OOM.c. Okay. Yeah, the program how to write it very simple. Okay. Remember in your mind. Okay, every time you go to Apple Store to run this. While one. All right, you have a pointer. Okay, so let's try something easy. Every time I allocate one map, 1024 times 1024, 1024. Okay, every time I allocate one map. Okay, many people tell you that hey, the malloc return value may be null. Okay, so this time we will have a chance that this is null because we may run out of memory. Okay, so we will try to say using p error. I think I should tell you what is p error, right? P error is a kernel generated error. Okay, so when the p error happens, I will pause the program. Okay, to let you see what is going on inside the memory layout. Okay, so I better also print out this PID early. Early is not good. Okay, maybe by the time it stops, okay? I also print out PID so that we can together go to see what is going on inside. So what do you need more? Maybe we also add a counter, right? Counter to count how many map I allocate. Yeah. Okay, so I will click on saying that how many map I allocate. Okay, so is there anything missing? No. Wait, no one tells me. Where? PID? Oh, yeah. Yeah. Why you know then don't tell me? Okay, so it's just complain about I didn't include some or header file. Yeah, don't care. Let's go. Do you believe that? 1 second, not just 1 second, it's half second. I allocate 3,000 megabyte, 3G, and then it stopped and telling me that malloc cannot allocate memory. Do you believe that this is just true? Or is it because our deployment machine is so powerful? Let's check. Suspend. Top -P 18581. So do you understand this report? This report, this area is talking about memory allocation. And this is a priority, this is nice value. This is the allocation of memory, CPU, okay? Do you find anything wrong on this report? Can you find, what is that? Is it VG? Yeah, it's VGB. But can you see the percentage of memory usage? Does it match? Or our department computer is so powerful that at LP 3 GB is still 0.1%? You believe it? No, I don't believe it. Yeah, let's see it here. How many? You're very few. Yeah, it's not matched, right? Yeah, something wrong. Something wrong. Okay? What's wrong with that? Now, this time I'm going to be very careful. I don't care you, okay? I will KO you. How about this? Do you know what this statement means? No or yes? Or really no, okay? I really make use of the memory. Sorry, Python. Yeah, it's just complain about it. Then, okay? Oh. It seems that something different this time, right? Really different. Now, how about I do this? Okay? If counter equal to 3000, okay? Then I pause it, okay? So that we can see what is going on. Okay? So if it's 3000, I pause it. Hope that I won't kill that guy. Okay? So now the process just stopped there because of our LK 3000 now. Okay? Let's see what is going on if I suspend it. What can you see this time? What is the difference? Is it quite different from last time? Okay, this spot, what are the difference? Anybody? What are the difference? Memory percentage, what is that this time? Yeah, 1/3. Really make use of it, right? And can you see the VIRT column, because virtual allocation column? Virtual allocation column is still something good or bad? Yeah, still expected, right? But the REX column, we call it resident memory, the memory really resident that is in the physical memory area. Now, it's different from previous time. Totally different from previous time. Now, what can you say about this program? That's why I use the 32-bit CPU to test it. Also, I will explain why. Okay? And remember, don't fire up this program in any 64-bit CPU. You will regret it. Okay? Later I will explain to you why. Okay? So, yeah, somebody already know what I'm going to talk about. Make a funny sound, huh? Now, okay, stop there. Okay, so what can you say about this program? This program is fast, really fast, but no use at all. It's not really making the real deal with the kernel. The kernel is just giving you a false hope, actually. Just like what you tell me, okay? Yeah, you tell me I will do the assignment, no problem. Okay? Yeah, but are you really doing? No, okay? This is the same. You ask the kernel give you memory. The kernel say that, okay, I give you. But it's not really giving you memory. This is a false claim or false hope, okay? The chance is you can grow your allocation within your process, but whether this is a physical memory given to you is by the time that you make use of it. If you use it, kernel will give you. Okay? So then I make a lies. What is the lies I just made? Okay, so I have this program. Let me do a copy and paste. At the middle, copy. I make a lines here. No, what I say? Is this very too big? No. Very too big, guys. Okay. Good. This is very big. Yeah, I disabled the copy and paste block. Okay. Yeah. Later during the break, I type it. Okay. Actually, I make a false claim is even though you don't have the enough memory, you write and launch this program, it still works. As long as you don't claim that memory and want to use it. Okay? And other version of this OOM program is I just change a bit. Where's the bit that I want to change? Okay? Later on I will revisit this statement. The claim is I do something change here with more stack allocation and more global memory allocation. Okay? Will that affect my memory allocation in the heap? Yeah, do you see the difference between this and the previous time? The previous time I don't have a huge global variable, I don't have a huge stack variable. Now I introduce two variables there. Will it affect my allocation? Okay? So that's why I don't log out. I don't log out from my department. Because I will relaunch the EC program, okay? Yeah, I comment. Then I add a big enough stack, okay? Big enough stack, I call it S 8000 times 1024. All right, I have 1024. Okay. And I will also have a big variable in a global area. Would be 2. 2 is too big. Okay, 1 gig. Okay, 1 giga. 024. I think I didn't say so many. 1024. 1024. 1 giga. So 1 giga space of a global, approximately 8 meg from the stack, and then see how it affects your malloc area. Voila. It's consider me I use it? No, I didn't declare that. Maybe let's pick 0. It still takes me so many time. Strange, you know. That Linux sucks. Yeah, seldom say Linux sucks. Okay, go. So previous case is 3000 something. So that's why I set a block there, 3000, then I stop the program. Now it's a spiller. So what can you say about this? What can you say about this? Okay, maybe I go this direction. What can you say about this using this map? The allocation in a heap. Basically, add together with the robo, with the stack, become constant. Right? You have a bigger area in robo, then you will have a smaller area for the heap. If you have a bigger area in the stack, that will also affect the area for the heap again. Now, because the stack is too small, you cannot see it. Now, someone help me remember the last number, 2028. Okay, I have a very short-term memory here. Okay. So, comment it. No 028, huh? Okay, run. More. See, if I say that I don't need so many heap area, then I can steal their unused area and claim it and put inside my heap. Okay? So what can you say? This area add together is actually a constant. Okay, and I only can demonstrate it for bit CPU. Because 64 is a huge area. Maybe I need 1 hour to conquer every addresses. Okay, and of course, okay, nope, here. Don't run this program, huh? This program is extremely dangerous. Next time, I will bring my EPC to demonstrate. Yeah, that is for, the EPC is for that using. I will bring my EPC to show you what happened if I have 2 OM, 3 OM noise together. Okay, whether you will get killed or I will get killed, yeah, very interesting. Or whether your computer will be booted, okay? Yeah, so let's have a break. Let's have a break. Okay. Yeah, so last demonstration, right? Although this number I write down should be several years before I write down this number, but it still works, right? It's because with the 32-bit CPU, okay? Last time I already said that in a global area of memory, okay, we cannot allocate more than 3 GB. It's still the same reason. Okay, the reason is again here the highlight area. For Linux, no matter if it's 32-bit or 64-bit, it will reserve some of the space. Okay, the space is for its internal use, and you shouldn't touch it. And that's why if we have so limited area with the 32-bit CPU, it will also hit the bar if you kind of want to allocate more and more and more. Okay, so this is the results why we always see this, and also explain this second version. If I grow a bit, okay, let's say I grow 1 GB in this area, the global area, then I will have 1 GB space loss when I'm doing the infinite loop malloc. Okay? So this is not very hard to understand because this add together is a constant. Now, it's time for me to teach you what exactly means segmentation, or I should say, how can you generate segmentation plots? Okay? You guys want to avoid it now, but after you understand what is the heap, what is the step, what is the verbal, especially for the heap, right? You understand why you have segmentation plots when you're using 3. Why you are having a problem is because you corrupt your linked list, okay? And the linked list will be used every time you got a 3 call, you got a malloc call, and that's why you get something wrong. And this is general sense on how to look at segmentation plots. General sense. It is usually someone, okay, maybe a year 2 or year 1 teacher. Okay, I mean the teacher is not from year 1 and year 2, but teaching year 1 and year 2 course. Okay, tell you when you access a piece of memory that is not allowed to do so, let's say the read or write. Okay, then the OS will return you this segmentation plot error. Okay, now this statement has a several mistakes there. What is the meaning of sex? Okay, we have read, write, execute, right? The several kernel in case they execute a memory. Okay, we read, we write, and is it really the OS or the CPU? Okay, so we will show you a map, okay, and try to explain to you approximately how many ways to generate segmentation plots. Okay. The map is just one that I showed you. I only tell you to see this area, but I didn't tell you to see this area. So let's take a look at this purple area here, not the block. Right? The purple area, some area you already know it, but 2 areas are now I newly included there. The unallocated area for a stack, unallocated area for a heap. Okay? Now you understand that because of the previous demonstration, this unallocated area belongs to these 2 guys, but there is no clean cut there. So what is the meaning of clean cuts? It's not always the allocated stack plus unallocated stack equal to 8 MB. It's not true. Okay? You can have a very hungry allocator using malloc, keep on allocating every possible area, and take all the 3 GB memory so that if you want to call function, you won't have enough space. Okay? So that's these 2 guys won't add together give you 8 megabyte. But these two guys add together, the max is 8 megabyte. Okay? And this area is even more passive. Passive in the sense that it has to see how many holes or how many areas that other guys leave for you. Okay? This guy, yeah, I think there's someone raised their hand. Yeah, oh, okay. This guy gets stuck. Okay, I'll cut this out. Okay? This area can define a big area while I'm writing the code, okay? Then you will have a smaller unallocated heap, okay? Or I should say that, why I say passive, only after the code being compiled, you can only guess approximately what is the space here, minus approximately 8 megabyte, because this area can grow before you call malloc. Okay? So this two guys has a race, and the race is in this direction. The stack grow in this direction, really, okay? It's grow from big address to small address. The stack is growing in this direction, and heap is growing from small address to big address direction, so you could go these two ways, okay? And this two area is just like a foundation, okay? We have a big foundation, then this inherited source becomes small, and let's say we have very few global, then we have a very huge gray area. And why in these two ways? There's actually right region in terms of a memory address. This is just an illustration. If it's for memory address, you will find 0 here, the small address. And let's say this is a 32-bit CPU illustration. H0, F will be the biggest address that is possible to have. So you will have this allocation like this. Okay? So this is an illustration, and now what is the meaning of segmentation faults? Segmentation faults, the meaning is, depends on your operation, you are reading a code or writing code for reading, okay? Writing code for reading or writing code for reading or writing. Okay? Then we have some yes, no here. Yes or no means whether you got segmentation faults or not. Okay? Let's say there is two areas I didn't explain. There's area called unusable area. Okay, some area that the kernel shield from you that you cannot touch. There's a reserved for the kernel. And one of the special address also reserved by the kernel is the 0 address. Do you know what is 0 address? 0. What is that? Now, that's why the dereference null pointer is at 24. Okay, it's reserved as an unusable address. So whenever, no matter you're going to read and write an area of an address, which is fall into this unusable area, segmentation fault. If you have an address which fall into the code and constant area, now depends on what you're going to do. You want to write it, segmentation fault. So I give a yes here. If you don't want to write it, you want to read it, no problem. Okay? Others are quite safe, right? Others are the data, the DSS, okay, the allocated heap area. You have an address. Fall into this area, you dereference it, read or write, no problem. Okay? And what are the remaining areas that you will generate some guaranteed segmentation faults? Unallocated zone, the zone that you didn't allocate for it. Unusable area above the stack. Okay, so this 1, 2, 3 is a certain depth. Okay, when you try to dereference a so-called address there. Okay, now you get some picture here. Now I ask you why you get segmentation faults. Some scenarios because of malloc and free. Now we contour it. Let's say you're writing some code, you're writing linked list, okay, and so happens that you get segmentation fault during the time you write a linked list. Is usually because the content of your address point to some area that is fall into this yes. Okay, this yes. But looking at this diagram, you'll think that yeah, there's only 1, 2, 3, 4, 5, 6, 7 yes. Okay, no is more than yes, yeah? It doesn't mean that you have a low chance of segmentation fault. Sorry, this area is not on the scale. This is a huge area. The unallocated area is huge, okay? Imagine that in a 64-bit CPU, this area is just a gigantic size, okay? So it's very easy to hit the area. If you get a random pointer address, you try to reference it, you try a lot, whether you are inside this allocated area. If no, sorry, segmentation fault. Okay? And this is also why you dereference null pointer, you get a segmentation fault, because the null pointer is the area fall into the unusable address got by the kernel. Okay? Now, with this knowledge, I will start to have a program that's very formal, which is make use of segmentation faults to measure something. I give you 2 minutes to discuss with your neighbor. Take a look at this program first. This needs some time for you. What this program is doing. No fork, no execute, but I have a handler to handle segmentation fault signal. So when segmentation fault generated, I will stop the program. Take a look at this program. What this program is doing. Oh. Yeah, effective use of segmentation faults. What I'm doing. Oh, by the way, also answer me several questions. Will this program stop? What will this program stop first of all? Or I should say, will the signal handler get involved? Okay, because when the signal handler gets involved, you will call exit. Then the program will stop. Oh, by the way, after I write up this program, I found exactly the same program appear in one of the books. The book is written by a group of Japanese people. Nope. Let me check. Nope, it's gone. It's gone. Or maybe this book is too dangerous. Okay, if you want to take a look at that book, it's in my office. Okay, the book is called Binary Heap. Okay, yeah, it's the same program appeared here as well. Okay, what is this program is doing? We'll stop. To think that this program won't stop. Okay, so when it stop? Yeah. What's your answer? Okay, touch 0. How about you? Reach the what? The cosine. I showed you the previous slides, okay? You use the previous slides.
Yes,
I just go, okay? So his answer is reach 0. So go to 0, that will stop you. Unusable. So go to this area. So it means this boundary.
Yes.
Okay? So it's quite different, right? One set the lower boundary, one set the upper boundary. Any versions other than this two? No. Others don't know what this program is doing. Okay. Yeah, this program is actually what it's doing is, yeah, his answer is correct. The upper bound, not the lower bound. Okay. Oh, sorry, wrong direction. So I start this pointer equal to main, which is a part of the code. Okay, it's the code. So I read the address, store it in pointer, PTR type is char pointer, no problem. Okay, then I start the decrement of it. Every time I decrement it, I dereference it using the read capability, right? I want to read it, okay? Read and then store it in the C, okay? As if I'm going through this, start in this area, go down, go down, go down, go down, go down, and boom, I touch this boundary and cross that boundary. Then no matter it's read and write, segmentation faults. Okay? So this is a crazy, really crazy program, right? I'm measuring something, the bottom of the code segment. And you can see this program runs. Yeah, program is the code start. So same program, huh? Code start. So it's just stop there. And I also asked you to run one more program, which is also, I don't think it's available in Mac, but available in Linux. It's called pmap, to read the memory map of this program. And you can verify my answer got by this program with the system command, whether they match or not. Okay? And if you don't understand this, don't get frustrated, because you have a second chance. And that's not in the final exam. Okay? The second chance is in the next set of the notes. The next set of the notes is, I want to do another measurement. Okay? You can think of for a while during the weekend. I want to measure the upper boundary of the allocated heap. Yeah? How can I do it? I want to measure this upper boundary. I want to know where will I get the segmentation fault. If I keep it advancing from the heap and go beyond it, touch the allocated zone. Yeah? You can think of it, and it's in the next set of slides. Okay? So, summary. This is an interesting chapter. Interesting in the sense that I disclose many secrets. The limits, how can you make a full use of your program? The reason why you have free call and you try to avoid it. Don't tell other lecturers. Lecturers may think that you're telling people to write bad programs. For me, I will try to avoid it. I will use global variable. I build my own data structure. Okay, or even I heard of some companies like Octopus. Okay, I have a friend in Octopus. They try to avoid using malloc, not because of the dangerous features like that, corrupt the linked treaties, but I think from a perspective of performance. The link is there, you're scanning it for Octopus, it's not acceptable. Because while as you put it there, within 0 something second, you will take it off. Okay? So within that area, I need to finish the malloc, the free, all the ways. Yeah, forget about it. That's hard code. Or not hard code, but you PLK. Right? You PLK something without using malloc and free. And that is their way to implement it inside an embedded system. Okay? And of course, sometimes the malloc space is smaller than the required, okay, because you are overwriting something, and I love this conclusion. Sometimes you write to some unknown area, it's no problem, or usually you'll say that, in my home it's okay. In my home computer, no problem. My answer is, you are lucky. Okay, just because you are lucky. Okay, and I don't know why during the time that we have a demonstration, then you are lucky. Okay, get review. Why is get no problem in my home? Okay, yeah, it's because you just have a random number, become a pointer, assess it, no problem. So happen to hit some no problem area. Okay, so to see whether you have a luck, you can refer to this table. Okay, so this is an interesting point. We have still 15 minutes.